All right. All right. All right. So we were looking at the beginning of spring mass systems, which is we're just going to start with horizontal spring mass, no friction, just the spring force. So F equals ma only consists of F sub s, which is just the spring force. What is this? And so the spring force we talked about comes from Hooke's law. It's negative kx, where k is the stiffness constant, x is the position, x being positive to the right of the, so in this case, the stretching the spring corresponds to positive position, and the spring force acts in the negative direction. So it tries to restore back to its natural spring length. So you have just a simple homogeneous. So once you push this negative kx to the other side, you'll get a homogeneous equation of this form. It's just a characteristic equation. It will give you some roots. It'll always be complex roots in this case, just because the k is always positive and m is also positive. And you'll get your solution, and then you have some initial condition, which might be like, I'm gonna shove this a little bit to the left initially, which means that the spring will be compressed a bit, and then it was giving a gentle nudge to the right, and those conditions will be like what you'll use to find C1 and C2, and then you plot that with no friction. This thing will keep oscillating back and forth. It's just basically gonna go back and forth, so there's like a natural equilibrium length, but because it's like really slippery, once you shove this down to the left, it's gonna compress the spring's gonna push it out. If you also put a force towards the right, like the purple condition here, then it's going to go past the L position to a certain extent before the spring actually is going to try to pull it back again, because it's proportional to the length that the spring is being compressed or stretched. And so it'll keep doing this over and over without friction. But you wanted to figure out, like, what are some things about the motion that you want to be able to describe, like amplitude, the frequency, the period of the oscillations. And so the way it's written like this, it's hard to read that kind of information directly. So you might take this and rewrite it in a form that's a single sinusoidal function, so a single cosine function. Then this capital R that's in the front will be the amplitude, and then this little phi here is called the phase angle. And in order to force this original form of your solution to look like this thing right here, you would need to figure out what the capital R and the phi would have been to make this true. And I'll note here that these omegas are the same. So these omegas are the same, like this omega naught, and this omega naught, the same. And that's okay. It turns out to be those being the same is fine, because if you use the double angle, well, not the double angle, the cosine subtraction formula to rewrite this thing that's underlined in red right here, then you'll have R cosine of omega t minus phi. This thing expands to this. And then I'm just going to say, okay, this thing right here has to equal this thing that's underlined in purple. And in order for that to happen, we must have had C1 is equal to R phi, and C2 is equal to R sine phi. And we notice that those are basically R and phi are your polar coordinates for the Cartesian coordinates C1 and C2. So if somebody gave you C1 and C2, then this relationship, like C1 will be your X coordinate because it's like R cosine of phi, and C2 is like your Y coordinate because that's equal to R sine phi. So the idea here is, like, we know what's underlined in purple here because that's what we have up here, but we're trying to rewrite this in this form. So we know C1 and C2, we need to find R and phi, and those go into these spots right here. And so if we know C1 and C2 are your Cartesian coordinates and R and phi are your polar coordinates, you can just, I guess I'll just move this over, but you would just draw, you literally draw the coordinate plane. So you'll say like, okay, we have this coordinate plane, and then you just plot your C1 and C2. So for the problem we just had, our you could just read off right here from here that our C1 was equal to -1, because that's right here. Well, I guess it's up here already too, but you can see from here that C1 was -1 and C2 was 1, because those are the coefficients in front of your cosine and in front of your sine. It's like the convention is what's in front of your cosine and what's in front of your sine is C1 and C2. So we're just gonna take those and interpret that as your Cartesian coordinates. So I'll just like paste it right here so that we have it. And so we're gonna interpret, oops. We're going to interpret that as our Cartesian coordinates, which means that I'm just going to plot, which just means that, okay, so I'll just write it like this. So you can think of a C1 and C2 is your Cartesian coordinates -1, 1, which is like this point right here. So you're like thinking of how do I describe this point right here in polar coordinates? It's going to be like the distance r, which is going to be the length of this thing, and then the phi would be the angle measured from the positive x-axis. Remember, this is the Cartesian. I mean, this is a polar coordinate. So we said that r is easy to compute because r is just the distance. So r would have been, for this one, like I'll just write it again here, r would equal, you look at the coordinate here, so use the distance function formula for this is going to be, this is basically the Pythagorean theorem, it's going to be -1 squared plus 1 squared, all under a square root, which of course -1 squared is 1, so this would just be 1 plus 1 under a square root. So this is the r. And then this one's a nice enough point that you probably can tell what phi would be using in radians. Does anybody have an idea? So this right here is pi over 2, 0. This is pi. This looks like it's halfway between pi over 2 and, yeah, 3 pi over. And that's exactly what we see here. So we see here, now that we found the r and the phi, we're good to go because this is like our r. And again, like these omega naughts, this omega naught and this omega naught. So like for this problem, I'll just say omega naught was equal to 4, right? That's like these right here, just like these right here. And it turns out that that goes right here. So that's why we have the 4 here is your omega naught is the same as the 4 that's here and here. And then the 3 pi over 4 is like the phi right here. So it's the phase angle. So that's why we have this right here is the phase angle. And that's it. You've rewritten this thing right here is equal to this right here. And we've successfully found the r and the phi that would have forced this thing to equal this. So basically, we're like saying this has to equal this. What must C1 and C2 have been? Using the subtraction formula, we expanded this. We come, it's basically matching. So I said, like, these are the terms that have cosine in it, has to match with this one. And these are the terms that have sine in it, has to match with this one, which concluded that C1 and C2 had to be these things, our cosine of phi and our sine of phi, which happens to be the polar coordinates for the C1 and C2. If you interpret C1 and C2 as your x and y Cartesian coordinates. And to convince you, I just graphed in Desmos the original graph is this right here, sine of 4x minus cosine of 4x. I mean, it's basically this in the in a different order, but it's the same. And then I said, I plot that in red, and then I said plot in green r cosine of wx minus p. W is like my omega naught, and then P is like my phi, which is like the phase angle, or the phase angle. And I said, well, make R equal square root of 2, like we computed, omega or W equal 4, and then P equal 3 pi over 4. And you can see that the green line, there's no red line because the green line's right on top of it. So both these plots are on top of each other because we've selected the R and the phi correctly to make sure that they're equivalent. And so those are that's how you can figure out what the amplitude and phase angle of your oscillation is. Some people, they like to write it this way. Like if you remember from pre-cal, you can like factor out a 4. If you factor out a 4 from both of these right here, this was 4t, so you only have t left. If you factor out a 4, then you need to compensate for that by multiplying by 1/4. So the 3 pi over 4 becomes 1/6. And this is called the phase shift. It's different than a phase angle. So I'll just say the phi is the phase angle. If you remember from trig, like this, if you've written it this way, it's easier to tell because what it does is it will the 4 will actually shrink your horizontal shrink. It's kind of like works opposite, even though it's like multiplying by 4, you feel like it would stretch, it actually shrinks it. And it shrinks the cosine graph by 1/4. And then the negative 3 pi over 6 just means to shift it to the right, even though it's negative, to the right by 3 pi over 6. So I'll just like make a note that that's usually what people like do to people might write it like that so that they can easily see what the transformations on the cosine function are. But if you look at this, this is actually, because I do have a blue line here that has a label here is 3 pi over 16, which is probably hard to see, but it's just trying to illustrate that this actually has a phase shift of 3 pi over 16 on a graph that's been on a cosine graph, because a cosine graph starts, I mean, from the origin, it has a peak at the origin, right? And then it looks definitely compressed horizontally. That's because of the 4. And then the negative 3 pi over 16 is just shifted to the right by 3 pi over 16. So the other thing to notice about this graph is that the amplitude, so that means like how far it goes up and how far it goes down, is given by the square root of 2. So if you like say the r is square root of 2, so that means r is square root of 2. So that means like this is the extent that this thing goes up and down. So this is like 1.5 right here. So if you did square root of 2, it'll be like something like just under 1.5. So that's describing how far. So this is position of the mass. It's going to be like going all the way past the natural spring length by pi over, no, not pi over 2, square root of 2, and then goes all the way back by a distance of square root of 2. And that's the maximum extent that it actually goes, stretches or compresses beyond its natural spring length. So there's other information that one might want to extract from this. So we see the amplitude is R. That's, I'll just write that up here and just say this is amplitude. So you might be interested in different things like so the period of the oscillation, so how long it takes to go out and come back is going to be there's an omega naught. This 4 pi this 4t is the this 4 is the omega naught, and so if you remember from trig, it's going to be like 2 pi over omega naught. So in this case, this 4 is going to do a horizontal compression to this graph, which means your period is going to actually be smaller. That's why it's like normally your cosine graph has a period of 2 pi, but because you compressed it by a factor of 4, it's going to be 2 pi over 4 is going to be a period instead. Frequency is, if you remember, is how much times it oscillates per unit time. It's going to be the reciprocal of the period. So it's like omega naught over 2 pi. That's just a reciprocal of this. And then we already know amplitude is, so it turns out that no matter what you have for your C1 and C2, like it's like your X and Y coordinates, Cartesian coordinates, the distance formula or Pythagorean theorem will always result in just an amplitude that's C1 squared, C2 squared. So these are some things that one could extract from the solution. So for the problem we were looking at up here, I wanted to also talk about units. This is like grams. This is grams per centimeter squared, centimeters per second. Okay, so the units would have been a period is a unit of time. It's like saying how long will it take for it to like do one thing. So for the problem we just had, this would be seconds. I mean, they could be minutes, it could be hours, depending on the units for the problem, but I'm just going to use the units for the particular one we just did. Frequency is what's the units for frequency? Yeah, it's per second for this one. So it's going to be like basically the reciprocal of, so it'll be like frequency is 5 per second, 5 oscillations per second. Per second is, I think, called hertz. What's the amplitude in this problem? It would have been centimeters. That's just saying how far it moved out and came back. That's like the amplitude. So those are the units for our particular problem. Yeah, I think that's all I wanted to say about the amplitude phase form for now. It's just a way to rewrite something that's you're usually going to get a solution of this form, because when you actually solve the characteristic equation for homogeneous second order equation, you'll get something like this, where you have two separate trig functions. But if you want to combine to a single trig function, the benefit is that you could read off the amplitude and stuff. Things that you would have maybe not been able to tell just by looking at this directly, like, oh, the amplitude of this is square root of 2. Now it's really easy, because if somebody just asked you for the amplitude, like let's say they don't even ask you for writing it in the amplitude phase form. They just said, solve this problem, mass is displaced by this, there's this spring constant, blah, 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 solve it, and then tell me what the amplitude of the oscillations are. You would do all this, and then just take the C1 and C2, just square both of them, add them together, and then take the square root. You don't have to go through the trouble of actually finding the phase angle in that case. So, that's it. But at least you see that connection. And that would be the way you would compute the amplitude. So I guess I'll also mention something else here. This omega naught here is also something that you can easily find even before you actually you could get that immediately by noticing that in general, if you have no damping, so like in this case, like our equation was this without damping. So I'll just grab this. So without damping, we just have this spring force, and we found that this was the equation. And so for any m and any k, you can always just solve this, and it will always be like, I'll just say that you could just divide both sides by m. So you'll just get x double prime plus k over m times x equals 0. Okay, just divided everything by m. And then you just do the characteristic equation, which is r squared. And then this skips at x prime term, so it'll just be over km is equal to 0. Then you'll get r squared is equal to negative k over m. And then this will always mean that your r is equal to plus or minus I square root of k over m. K and m are always positive, because you can't have negative mass, and you also can't have negative stiffness constant for the spring. So this will always be true. And so what this means is that you'll always have, omega. Well, why don't we call this? Why don't we say that, let's say this right here, I'm just going to redefine, I'm just going to say this is I. Use a different, more darker orange. I'm going to use this and then call this omega naught. So why don't we just, this is what they say. They say like omega naught is just the square root of k over m. So then in that case, I plus or minus I square root of k over m. If we say omega naught is equal to this, would just equal plus or minus I omega naught, which clearly means that this is just pure imaginary. So beta is equal to omega naught. And then we'll just have, we'll just have our solution is going to equal C1 cosine of beta, right? There's no alpha, so it would just be this beta, which is omega naught t plus C2 sine of omega naught t. So for all these problems, for a spring mass system with no damping, your mass is always positive, your spring constant is always positive. Your characteristic equation will always give you plus or minus I square root of k over m. And if we say omega is equal to square root of k over m, then that means that your solution will always be like your general solution will be C1 cosine omega t plus C2 sine of that omega t, where omega naught t, where that omega naught is equal to the square root of k over m. How does this look like with the previous one? We did through all this work, but for the one we had up here, we could have seen that omega naught is equal to the square root of k over m. In the problem up here, k was 48, m was 3, so it would have been square root of 48 over 3. 48 over 3, so if you just divide 48 by 3, it would have been square root of 16, which is equal to 4, which is what we see here. And so some people, they just read this problem, they know there's no friction, so they'll just say my answer is going to be C1 cosine of 4t plus C2 sine of 4t, where that or what the omega naught t and omega naught t, where those are just equal to square root of k over m. So in some books, you may see like that for simple harmonic motion, the solution is always going to be cosine of square root of k over m times t plus C2 sine of square root of k over m times t. Right. And this has a name, so I'll just say this omega naught is equal to, I'll just I'll put a orange circle around or box around it. If this convention is, this is like a standard thing where they say omega naught is just the square root of the spring stiffness constant over the mass. And that omega naught is called the circular or angular frequency. It has some connection to the frequency of the oscillation because this omega naught that's being multiplied to the t inside these trig functions is going to give you some, is going to have an effect on the frequency. It's called circular or angular frequency because if you look at, let's say, let's just look at what we had here. Frequency is this, right? So I'll just go up here and say, what if we solve for omega naught? Then we'll get omega naught is equal to 2 pi times the frequency. I'll just use F for frequency. So omega naught is 2 pi times the frequency. Frequency is the amount of times. You may have seen this. So what it's doing is that it oscillates this many times frequency per unit time, but we're just multiplying by 2 pi. So it would just been like, instead of how many times it oscillates over unit time, it'll be like how far it moved around the unit circle, because 2 pi is the circumference of the unit circle for a unit time. Okay, so if it's a frequency of 1, then it'll be like 2 pi, which means that it moved around the unit. That's the distance it moved around the unit circle. That's why it's called circular frequency, or some people call it angular frequency. If you think about like, this is like radians around the unit circle. So that's why it's called that. So interestingly, if somebody asks you, like for the problem we just had, like this up here, this one asked you to find the expression for its position as a function of time. But if somebody just straight up asked you, what is the frequency of the oscillations that you would have, then you could do that without having to solve all this, right? Because if you're interested in just computing the frequency, then the frequency was what? So let's just look at it. Omega naught over 2 pi, right? Omega naught over 2 pi. So the frequency would have been omega naught over 2 pi. So then you compute omega naught like this, right? And so you'll just say omega naught is square root of k over m. That's equal to 4 over 2 pi. And so this is just equal to 2 over pi hertz. And so you could, like, for a system with no damping, just the mass and the spring constant, then you could just do this, literally just do this to compute what the frequency of your oscillations would have been. Because what did we find at the end of all this? We found that frequency is just omega naught over 2 pi. And I just told you that omega naught for this will always be square root of k over m. So you can just use that without having to actually even solve anything. Right? And then the period would be just the reciprocal of that. And the amplitude you have to do a little work because the amplitude is actually solving all this, then applying the initial conditions to find C1 and C2. And so you would have to do the whole thing to be able to find the amplitude. But frequency and period, you actually just needed to find omega naught. And for these problems in general, they'll be a differential equation of this form where the characteristic equation will always spit out this square root of k over m. And so, and that goes into these, and those are omega naughts from all this. So that means that you'll just have to do that simple calculation. Okay, so that's without friction, but in reality, they'd be friction. So you still have the same horizontal spring mass system, and there could be friction or other resistive forces like air resistance. And the physics for resistance is similar, but applies in to something different about the object. So with the spring force, I'll just like go back up and say, okay, what did we say? It was negative f of s is equal to negative kx. Let's just write that. F of s is equal to negative kx. Let's just compare what the difference is between that and the resistive force. So F is equal to negative kx. They both have a negative sign, but the difference is, of course, they have a different delta. So delta is called the damping constant. It's not a derivative. It's just a delta. The Greek symbol delta is what they use for the damping constant. That's basically how sticky your table is. The higher your damping constant, the more resistive your table is to motion. The K here is their stiffness constant. The higher it is, the stiffer your spring. They both have a negative sign. That's the similar about it. But what's different about it is this is X right here. So it's proportional to the position of your object. It doesn't care about anything but how far the spring had been compressed or stretched. Whereas this one has an X prime multiplied to it. And so the idea is that they're both proportional to something. Spring force is proportional to the distance the spring is compressed or stretched. That's why it's looking at the position X. Whereas the friction or resistive force is going to be proportional to the velocity of your object. So like if you were in a car and you stuck your hand out the window, which you shouldn't do, but if you did, and you were driving slowly, you'll feel like the air resistance against your hand. But let's say you were in like a NASCAR, like race car or something, like going really, really fast, and then you stuck your hand out the window, you'll feel the air resistance is much stronger, and it's because it's proportional to how fast you're moving. It's proportional to the velocity, and it's in the opposite direction. So you're moving forward, but the force that if you put your hand out would be like back, right? So, it's not like it's gonna. So like you're moving this way, but your resistive force would be, so it's opposite to the velocity you're moving. So if you're in the car, you're moving forward, the resistance would be pushing you back, your hand backwards, and it's proportional to how fast you're going. So the faster you go, like let's say if you were in an airplane and you like were taking off, then initially your hand, you could probably do this without much trouble, but depending on how strong you are, you're gonna feel the force, So that's so let's say so the convention is still the same here, where we're just saying like stretching is positive. So this is like greater than 0. And let's say that you were moving in this direction. So you're like your x prime is negative. So this is positive, still keeping that positive. Let's assume that this spring is actually going inwards, right? Going towards the wall. That means that you're moving to the left. So that means your x prime is equal to a negative thing. And then, but your resistive force should be this way. It's going to try to slow you down, basically. So if you're moving in the left direction, the resistive force is going to try to slow you down by going to the, pushing you in the opposite direction. So like, this is like, suppose you had x prime is less than 0, which is moving to the left. Then your friction force. Because this, I'll just make a point it out and say this right here, this x prime is negative, so negative times a negative is positive, so your frictional force would be to the right, force to the right. Okay, so that's the difference is that it's actually it cares only about how fast you're going. The spring force does not care how fast you're moving. It only cares about how far the spring has been stretched or compressed. It doesn't matter if you're how fast it doesn't care about how fast you're going. It just literally cares about I'm being stretched too much right now or being compressed too much, and I'm gonna apply I'm gonna apply an opposite force that's proportional to how much I'm stretched or compressed. So they look at they care about different things. So that's why there's a negative sign because it's opposite. So let's go back. F equals ma, and then we replace the a as x double prime, and then we shove rearrange, so we just get this mx double prime equals f. This is really just f equals ma, literally the same thing. And then this f is your total force of everything. So basically, we used to only have one force for this, but now we have two forces on this object. We have a spring force and a resistive force. So before it was just F sub S, but now we have an F sub R as well. We know each of these, right? F sub S is this, F sub R is this. So I'm just saying F sub S is negative KX, F sub R is negative delta X prime. Now I'm going to shove all these terms to the left just because they have x and x double x prime, and we like to have all our x to the left. This now results in another homogeneous equation with an additional term. The previous one where we didn't have damping, it was like this because it was only the f of s. It skipped the x prime term because it just had the kx term only, which is from the spring force. But the damping force appears as an x prime term in your second order differential equation. And so you have this extra term right here, this delta x prime. So this is an additional damping term. So this is just like adding a damping term into your second order equation, but it's still homogeneous, so you can solve these. These are not hard to solve because what you're going to have is, I'll just write down this equation. This is your basic equation. So still homogeneous. So I'll just copy this right here. Consider a spring mass system now with friction. Let the mass be 3 grams. Let the damping constant delta equals 8 grams per second and the spring constant equal to 4. That gives us this equation. So what does that do? This ends up giving us the mass is 3, so 3x double prime. Damping is 8, 8x prime. Spring constant is 4. X is equal to 0. All right, so let's solve this. Later, there's all these initial conditions we'll have to do. But if you use the characteristic equation for this, this will just be 3r squared plus 8r plus 4 is equal to 0. And this one doesn't factor really nice, but you could use the quad formula, Q formula. I'll just say Q formula. And you'll get r is equal to -2 and -2 over 3. Okay, so once you get those your r's, then you can write your solution. Your general solution would just be, this is distinct roots. So these are not complex, they're real and they're distinct. So you'll just have C1 e to the -2 plus C2 e to the -2 over 3 times t. And that's your general solution. And we just have a couple initial conditions here. We're saying that the mass is displaced by 1 centimeter to the right of the equilibrium position, which is the natural length of the spring. And then we simply let go. So it has an initial velocity of 0. So we're just moving it to the right, and then we're just letting it go. So if you have a horizontal spring mass system where it's like this picture right here, displacement to the right would have been positive. So that means that the initial condition is saying at initial time, we're just going to say it's at 1. So that's my condition on the function, and then this is the condition on the derivative. So it's saying x prime at 0 is equal to 0 in this case. We're just letting go, so it has an initial velocity of 0. So these are the two conditions that you need to use to solve for C1 and C2. We're going to have to take the derivative of this to apply the purple conditions. So I'll just go ahead and do that right now and say x prime of t. Just the chain rule. So it's going to be -2 C1 e to the -2t. Minus -2/3 C2 e to the -2/3 t. And then you're just going to apply these conditions. So you have x of 0 is equal to 1. That's like your first initial condition. If you have that, then you're just going to get that you need the function equal to 1. That means this is equal to 1 whenever all of this t's are equal to 0. So it's just C1 plus C2 because the e raised to 0 are. And then you have the other condition, which is x prime of 0 is equal to 0. This is like saying this derivative here is equal to 0 whenever all the t's are equal to 0. So it's going to be -2 C1 minus 2/3 C2. Well, you could just say that this is like C2 is equal to -3 C1. That happens because I could just move this over. That's going to be positive 2/3, and then I can multiply by 3 over 2. And so it'll be equal to this. Then you can go up and do substitution. So you can just say this is like 1 equals C1 minus 3 C1. And this is like -2 C1. So C1 is equal to -½ Okay, so that's that one. And then once you have that, then C2 is very easy because down here, you just get that C2 is equal to -3 divided by 2, but positive is going to be just positive 3 over 2 is equal to your C2. Okay, so that's just solving for those. So now you got your solution. It's going to equal this general solution, but with a -1/2 for the C1. And then a positive 3 over 2 for the C2. And that's the graph that we have right here. It looks a lot different than what we had up here, right? This one was without resistance, no friction, no damping. It was like a situation where it's really slippery and it's just going to oscillate. Like the thing will just go back and forth forever. And so that's why we had sines and cosines, right? So there's qualitatively a huge difference in the solution because you have sinusoidal like trig functions that we used to have up here when we didn't have any friction. But the solution form we have now is not even sinusoidal, it's exponential, and they're exponential decay. So how would you describe this? This is just saying that, of course, we have this condition, right? We have these initial conditions. So this is like saying, like, we need to make sure that at time equals 0, we're taking the mass and stretching it out and moving it to the right by 1. That's why the position is not at 0, it's at 1 initially. 0 is like the equilibrium position. It's the length of this natural length of the spring. It's like this L right here, like how far the spring would have been if you just let it go on its own. So we initially like pulled it out by 1 centimeter to the right. So that's why its starting position is actually at 1. But because we pulled it out, and then the other thing you should notice is that the initial velocity of this is 0. I mean, if you look at this graph, I think you can convince yourself that the tangent line is horizontal, maybe right there. That's just saying that I just pulled it and I let go without like nudging it or anything. But it's still going to move because you had pulled it, so the spring is going to want to pull it back. And that's why the object goes back to the 0 position, like the position of the natural length of the spring. But it moves really slowly, actually, because it's like, think of the table being sticky. So that's like friction, right? So it's like a sticky table. It just moves slowly. And because it moved so slowly, it just stops right when it gets to the equilibrium position. Whereas if it was slippery, it moves fast and it overshoots and then overshoots and overshoots and just slips back and forth. But with damping, think of the table being very sticky. You pulled it out, the springs want to pull it in, but it's going to move slowly and then just stop right there because the friction is quite high. So that's like physically what's occurring here. Now you can imagine once we have a differential equation that's mx double prime plus delta x so I'll just copy and paste this. You'll always get a quadratic. I mean, in the end, you can solve for the r using the quadratic formula, and it would have been like this kind of equation. So it'll always be like m r squared plus delta r plus k is equal to 0. That's the characteristic equation. And then you just use the quadratic formula. The quadratic formula is a negative b, which is like the delta, plus or minus the square root of b squared minus 4ac, so 4mk over 2a, which is 2m. Like, so let's just keep m and delta and k general, m being the mass, delta being the damping coefficient, and k being the spring constant. And your characteristic equation will be this. Your r will always be this by the quadratic formula. And there is going to be 3 cases: distinct real roots, repeated real roots, or complex roots. And it all depends on the sign of this thing inside the square root. So if the inside of the square root is negative, will you get real or complex? Complex. So that's going to happen whenever your delta squared is less than 4mk. So like if your delta squared is less than 4mk, that means your 4mk is going to be bigger. Then you'll have complex roots. If your delta squared is bigger than 4mk, so that's right here, then that means that delta squared is bigger. So you're just going to get something bigger minus something smaller. So you'll get positive, and that's going to be distinct real roots. They'll always be negative, it turns out, because the biggest you're going to be subtracting or adding is going to be by delta, and assuming that m and k are positive. And then if they're equal to each other, then you're going to do a plus or minus of a 0, and that's a repeated root. So you have all of these cases right here. What we just saw previously up here was distinct real roots, right? So you had -2 and -2/3. So we had distinct real roots, which means that this is like the discriminant was positive in that case. And if we had something that's negative right here, if this was negative, then there's going to be like basically your let's suppose this was negative, then you're going to get your alpha will be the real part. So the alpha will be like this. Delta, negative delta, there's a negative here. It would be negative right there. And then our I'll just write that had this been a complex roots, then it would have been, we already know the solution is like e to the alpha t times c1 cosine of beta t plus sine c2 sine of beta t. So if this was a negative number inside the square root, then the beta will basically come from this part right here, because this would be the negative part right here. So this will be like where your beta is going to come. Your alpha is going to be negative delta over 2m. That would have been the real part. So you're just going to have this alpha right here would have been negative delta over 2m. So it's going to look like oscillations that's multiplied by e to the negative delta m times e to the negative delta m, e to the negative delta over 2m times t. That's like an exponential decay. So it's like you have a bunch of sinusoidals multiplied by an exponentially decaying amplitude. That's going to give you this graph. So I'll just say complex roots will give you this, because this will be the solution for complex roots. It's going to be like the oscillations will still be there, but they'll decay. The reason it decays is because if you think about the spring mass without friction, very slippery, it'll just keep going. But if it's sticky, it's gonna start stopping. This is a case where your damping is not that high, because your damping was low enough that the 4mk was actually bigger. This is like you have a little bit of damping, but not that much. So the oscillations still stay, but they'll decay. And this is called underdamped. The other case we saw where it was really sticky and it just slowly came back to the original, that's called overdamped. We'll talk about this more next time. Yeah.